Applied nuclear physics demands a precise balance. We have to rigorously protect human operators from radiation while harnessing its power for life-saving medical procedures. Doing this safely requires mastering three specific areas: quantifying exposure with physical dosimeters, manufacturing exact radioisotopes in reactors or accelerators, and applying those isotopes as chemical tracers in living systems. Controlling this entire life cycle, from atomic production to operator safety, is the absolute baseline requirement for any modern clinical practice or biochemical research facility. Every protocol for radiation safety relies on diagnostic tools that measure exposure through exact, proportional physical changes. The most common tool is the film badge dosimeter. When radiation impinges on the badge, ionization within the internal emulsion darkens the film in direct proportion to the dose received. To identify specific types of radiation, the badge uses a configuration of 5 sections: an open window, 3 copper filters of varying thicknesses, and a lead filter. This allows the film to accurately differentiate between X-ray, gamma, and beta radiation. Other dosimeters use different physical properties. Thermoluminescence dosimeters, or TLDs, emit a measurable pulse of light upon heating that directly correlates to the radiation received. Meanwhile, fast neutrons produce distinct, countable physical tracks in the film emulsion of a dedicated neutron dosimeter. These measurable physical reactions provide the definitive proof hospital radiology staff need to confirm they are operating safely within lifetime exposure limits. Moving from measurement to production, the specific atomic manufacturing method chosen dictates exactly how a medical facility can use the resulting isotope. Reactor-based production bombards target materials with slow thermal neutrons. This triggers an N-gamma reaction, yielding radioactive isotopes of the exact same element as the starting target. Accelerator-based production fires charged particles, like protons or alpha particles, energized between 12 and 30 MeV. These targeted high-energy reactions generate completely different radioactive elements from the source material. This diagram compares the physical outputs. Reactors provide high yields of the same element, while accelerators produce lower yields of brand new elements, with notably short half-lives. Iodine-123 is a prime example of an accelerator-produced diagnostic tool. Created by bombarding tellurium with protons, it possesses a highly specific half-life of exactly 13.3 hours. That rapid decay rate makes it the gold standard for clinical procedures. It minimizes the total radiation dose the patient receives, while simultaneously simplifying the logistics of radioactive waste disposal for the hospital. Once produced, these radioisotopes are synthesized into labeled compounds. By deliberately substituting standard atoms within an organic molecule with radioactive ones, chemists create trackable markers. As shown in these naming conventions, specific labeling pinpoints the exact position of the radioactive atom in the compound, like the 5 in 5H-uridine. Uniform labeling uses a U, indicating the radioactive atom is distributed equally throughout the target compound. Synthesizing a carbon-14 labeled compound begins by absorbing radioactive carbon monoxide into an alkali solution. From there, substitution reactions integrate that specific radioactive carbon atom directly into larger organic acids or amino acids. Tritium, or hydrogen-3, offers an alternative labeling mechanism. Through direct chemical synthesis, researchers replace standard hydrogen atoms with tritium to create distinct radioactive variants of complex molecules. By applying tritium and carbon-14 as either uniform or specific labels, researchers can trace these markers through living systems, mapping exactly how a new pharmaceutical drug metabolizes inside a human body. Whether logging daily operator exposure, diagnosing thyroid conditions with accelerator-produced isotopes, or tracing metabolic pathways, this entire ecosystem runs on absolute precision. Mastering the physical reactions of detection, the atomic mechanics of isotope production, and the chemical synthesis of labeled compounds is exactly what turns theoretical nuclear physics into viable, life-saving medicine.